So now we'll take a look at vector addition, and even though we didn't explicitly call it out in the last example problem from the last video on vectors and unit vectors, this is actually what we were doing, just without naming it. So when we have two vectors, the way we add them is adding all of their components individually together. So let's take a look back at our example that we just completed in the last video, this vector a to b. So this force vector we found by using the positions of a and b. And if we want to, we can also label these as the vector from the origin to a. I'll label this vector a. And the position from the origin to b, which that should be a straight line, but you see where I'm going with it. So each of these two vectors we found by adding their components together, right? So to get the force vector, it was ax plus bx I hat. We add each component together when we're adding vectors, which is what we did in the last one, we just didn't explicitly call it out. By, and then there is the z component of a and the z component of b. So you add each component individually when we're adding vectors. Anytime we're multiplying by a scalar, as we did in the last one, where we had 2, 3, 6 over 7, that 7 got distributed to each value. So everything is broken up by components when we're doing things with vectors. This is going to be super, super important because we're going to be doing this all the time. We're always going to be breaking things down into their components and leaving them as x components, y components, z components. Sometimes we'll convert back to what the total force is, but a lot of times we're going to be breaking this down into their components so that we can solve problems with force vectors. Now, the way we most often see this come about is having forces all acting on the same object. So let's say I have a post here, and I'm tying my horse to the post. I'm tying my mini horses to the post. So I have one horse that's pulling on it this way. I have another horse that's pulling on it this way. F1, F2. And I want to know what the resultant force is on that. So what we're going to do is take our resultant force is just going to be the sum of the components, the sum of all of your x components of the forces, plus the sum of all your y components of forces, plus the sum of all your z components of forces. So we'll be breaking these down into their x components, y components, and z components, adding them together to get resultant forces. So we'll go ahead and try an example. All right, let's take a look at an example of how we would find a resultant force. So here I've got a little hitch on the side of my boat, and I've got 3 ropes coming off of it, each of them applying a force. So the way we're going to do this is we're going to break everything into its components, add them together, and get our resultant force. So we have 3 forces, and we have x and y components. There's no z, everything is just in the 2D plane here. So our resultant force formula for F is going to be the x component of F1 plus the x component of F2 plus the x component of F3 I hat plus all of the y components. So F1's y component, F2's y component, and F3's y component. J hat. This is an I hat. So all we have to do is use our trigonometric skills to determine what each of the components are. So if we look at F1, I'm going to go ahead and break it out a little bigger over here. So F1, we look at this triangle, we see it gives us these side measurements of 1 square root of 2. So I know that the x component is going to be this component right here. So to get our x component, all I need to do is take F1 multiplied by the proportion that is the x component. So that's 1 over square root of 2, which is the same that we would get from doing sine, tangent, cosine. This angle is the relationship. This is the relationship. 1 over square root of 2 is the relationship of the x component of the vector to the vector itself. So this is the same as fx over f. You can think about it that way. So our f1, all right, let me write this. f1x is going to be f1 times 1 over square root 2. And our f1 is 60 pounds. So that is going to be 60 over square root 2. The y component we break out from this triangle happens to be the exact same. Our y component is this 1 proportional to the force of square root of 2. So this is going to be, again, f1 times 1 over the square root of 2, which again gives us the same result, 60 over square root 2, which is 42.43 pounds. But it's really important that we pay attention to direction with each of these. So the direction of our y is positive because it's in the positive y-axis, right? Y is positive in this direction. But we notice our x is actually going in the negative x direction. This is the negative x direction. So this is not a positive value. f1x is negative 42.43 pounds. So let's write that out again. So we have f1x is negative 42.43 pounds. f1y is positive 42.43 pounds. Then we'll move on to our f2. So we'll draw out that triangle, for example. This one, we now see we have both negative x and negative y components. So this is a 30-degree angle. To get our x component, this is a negative x component. We use f2 times, this is adjacent to the angle, so we'll use cosine, SOHCAHTOA. Cosine 30 degrees. To get this adjacent value, this is the hypotenuse value, times cosine 30 equals the adjacent value, which is f2x. So f2x is going to be 70 times cosine 30. But remember that it's negative. So it is negative, what is cosine 30? Cosine 30 is not a half. Sine 30 is a half. So it's the square root 3 over 2. So you'll get negative 60.62 pounds. f2y is going to be the downward y component. So again, remember that it's negative. Now you're going to do sine because this is opposite. f2 sine 30, this is the one that's a half. Half of the 70 pounds is 35. Negative 35 pounds. I will add these to my top up here just to keep track of them. f2x is negative 60.62 pounds. f2y is negative 35 pounds. So now we have the very last one, which is very straightforward because it has no x component at all. All of the force is entirely in the downward y direction, which means that easy enough, this Easy enough. Our F3Y is going to be negative 50 pounds. And our F3X, there is no X component. It'll be 0 pounds. Now that we have all of these components, we can combine them together. So we'll add all of our X values. So our F1X plus our F2X plus our F3X. And then all of our Y components. Our F1Y, F2Y, and F3Y. So what we'll end up with is the sum of our resultant force is the sum of all X forces, which is negative 42.43 pounds minus 60.62 pounds minus 0. I hat plus the sum of all Y forces, which is 42.43 minus 50 minus 35 pounds J hat. So we add all of those together and we'll get our resultant force in Cartesian form. But our question asked for a magnitude and direction. So instead of giving them this final answer in the Cartesian form, we'll write that out right here just so we can keep track of it. It is negative 103.05 I hat minus 42.57 J hat. This is our answer in Cartesian form. Not what the question asked for, but necessary so that we can find what the question asked for. Now we can use this to convert into magnitude and direction. So converting our magnitude is just the same as using Pythagorean theorem, right? Our magnitude of F is the square root of the X component squared plus the Y component squared. So negative 103.05 squared plus negative 42.57 squared. So this gives us the magnitude of F is 111.5. 111.5 pounds. This is our magnitude. Now to get our direction, we will use arctangent, sorry. Because tangent of theta gives us opposite over adjacent, which is the exact same as just saying our Y component over our X component, the magnitudes of those. So the angle is arctangent of Fy, negative 42.57 over negative 103.05. Now we plug that into a calculator and we get 22.4 degrees. But before we accept this at face value, we need to recognize something. It's that both of these components are negative. Each of these is negative. And so if we were to draw this resultant angle, we would be getting a resultant force that looks like this, with an angle of 22.4 degrees at 111.5 pounds. Does that make sense? Does it make sense that we have exclusively negative X components, but end up with a positive resultant force? And the answer is no. What we need to do is we need to take this number and add 180 to it. Because both of these are negative, because our X and Y are negative, we know that our real resultant force should end up somewhere over here. This is where our resultant force should be. Because our Y is negative, because our X is negative, we know it has to be in that quadrant. So we'll want to add 180 degrees to our 22.4 to get what this angle actually is. This is the angle theta that we want. So we add 180 to that and we get 202.4 degrees. So this is our magnitude, this is our direction, and these two combined are the final answer. How do we feel about that? Let's do one more. Leave me any questions or comments you have below the video or in D2L, wherever. Email me anything you want to ask questions, we can clarify things. We'll do one more example, and this time we'll try it in a 3D system. Okay, so this is an example in 3D of being given a resultant force and having to backtrack and find one of the forces from it. So in this one, if our resultant force is 800 newtons in the J direction only. J, sorry, I just covered it up. This is the J direction, so the Y direction. 800 newtons in the J direction, find the magnitude and angles of F2. So we can see over here in our chart that, or in our diagram, that alpha, gamma, and beta have been written in for us to give us a sense of the orientation, but we have to find what each of those values are, as well as finding what the value of F2 is. So we know, go ahead and write it again though, that FR is 800 J hat newtons, which we can also go ahead and write, if you prefer the bracket form, 0, 800, 0. It just really shows us that there's no x component, there's no z component, it's all in the y direction. So the tricky part of this one really comes in with this F1 character here. We're going to need to break it up into triangles, which can be a little bit tough to see with these 3D diagrams. So I'm going to go ahead and break it out into this triangle first. This triangle, if we break this out, this is a 45-degree angle where we have a downward z component. This is the FZ component. But this downward side here is actually in the XY direction. It is not just an X component. It is not just a Y component. It is in both directions still. FXY. And then this side is our F1, the full magnitude of F1. So when we break that down, our F1 is 750. We get that the Z component is going to be F1 times sine of 45. Sorry, not sine, cosine of 45. It's adjacent. Cosine of 45. Which is 530.3 newtons. And our FXY is going to be sine. But note again, see, I almost missed it. I almost didn't write it down. This is negative. This is going downwards. It's a negative 530.3. And f of xy is going in the positive x direction, positive xy directions. So this is going to be 750 sine 45, which gives us a positive 530.3 newtons. So now that we have this fxy, we're going to use this triangle here to break down the x and y components. This is going to happen a lot when we have 3D systems. You may have to break things down more than once. You may need to use more than one triangle to kind of figure out how this sits in 3D space. So let's go ahead and break down that xy triangle. All right, so if we orient this xy triangle in space, we have this side is the fxy. It's being projected onto the xy plane. We've essentially eliminated the z component. That's taken care of. Now we're looking at this projection within the xy plane where I drew this a little bit wonky. Let me draw this triangle a little bit clearer, because that is not where the right angle is. The right angle is here. This is still 30 degrees, as we can see, but the right angle is actually over here. This is fxy because it's the hypotenuse. Just like in everything else, our fy is a hypotenuse, and then we're breaking it down into its coordinates, where this is fx and this is fy, which we can see fall along these lines, right? This is the y component, this is the x component, they fall along these lines. I just needed to reorient my triangle a little. So our fxy, we said was 530. 530.3 newtons. So now we'll break that down into its components. Fx equals fxy cosine 30, cosine because it is adjacent to the 30-degree angle, which gives us 530.3 times cosine 30, going to be 459.3 newtons. And this is positive. This is the positive x direction. And Fy is going to be Fxy sine 30, since it is opposite here. And that's going to give us 265.2 newtons. Okay, now that we have all of these components broken down, let's write it back out. So F1, as we found, the x component was 459.3. The y component was 265.2. And the z component was negative 530.3. All in newtons. So now we have the F1 and FR, but how do we find F2? Go ahead and pause the video and attempt to find F2. Now, even if you were only able to find F2 in Cartesian form, you're doing great so far. This is what we need to do. It's just going to be a straight vector subtraction. So normally, our resultant force is the sum of F1 plus F2. But in this case, we're rewriting it so that F2 is FR minus F1. So if we take a look at this, let's go ahead and, sub in our values. We know we just subtract components, right? So we're going to do F2 equals FR minus F1. So 0 minus 459.3 I hat plus 800 minus 265.2, that's our y components, that's the j hat, plus our z components, 0 minus negative 530.3. So this ends up being a positive since it's two negatives. That's our z component k hat. So this gives us that F2 is going to be F2 is negative 459.3, 534.8, and positive 530.3. This is the vector in our Cartesian form. You could also write it using the I hats and j hats. They're interchangeable. But again, it asked for magnitude and angles. So we're going to use this and backtrack to the magnitude and angles. So finding our magnitude of F2 is as easy as doing our reverse Pythagorean theorem thing, where we take the magnitude of F2 is going to be the square root of the square of each component. So the square root of 459.7 squared plus 534.8 squared plus, this is all under the square root, 530.3 3 squared. And we end up, if we punch that in a calculator, we end up with 882.2 newtons. That is our magnitude. Now the tricky part is, instead of like in a two-dimensional system where we would just have a theta angle to find, we have to backtrack and find 3 separate angles. We have to find alpha, gamma, and beta. Luckily, this isn't too difficult because we know that from our formulas before, that cosine alpha is fx over f, and same goes for cosine beta is fy over y. Cosine gamma is fz over f. So we have the magnitude of each. We can easily do the arc cosine of each one, fx over f, arc cosine fy over f, arc cosine fz over f, to find alpha, beta, and gamma. We'll go ahead and write that out real quick. So alpha is the arc cosine, the inverse cosine of fx over f. Our fx was negative 459.3 over an f of 882.2. This gives us the alpha angle is 121.4 degrees. Boom, that's one. Easy. Our beta angle, same process, now with the y. 534.8 over 882.2. Bam, there's beta. Plug that into a calculator. That is 52.7 degrees. And then our last one is gamma, which is our z component angle here. And that is 530.3 over 882.2. And that gives us our angle. Gamma is 53.0 degrees. So these 4 answers, let me do them in purple. These 4 answers in purple are our final answers. Now you'll find this is the way that a lot of statics problems are going to go. There's going to be multiple parts, multiple answers for things, but at the end of the day, all we're doing is breaking things down into their components. I want to look at all the x's, all the y's, all the z's separately before we can bring them back together into a whole. That's all we're doing. It's just the vector addition.